welcome everyone. Oh my, to widen my screen again. Go. So one little announcement, my office hours tomorrow, just this week will be 3 p.m. They're usually 2 p.m. And again, I encourage people, whether or not you have questions, just please come sometime. It's nice to get to know various people in the class. If you do want to ask a question, it can be about anything. It doesn't have to be so related to the course, or can go back to early parts of the course, ahead to things we haven't covered yet, whatever you feel like. Okay, so what I want to cover for the beginning of this week is Tedlins Theorem. Although this is really just motivation for something that I call the method of double cosets. So let's first start by stating what Tedlins theorem is. So let X be a, let's start out by saying that this is a compact hyperbolic surface. And then we have on the unit tangent bundle of X, we have the horocycle flow. And then the theorem is that every horocycle orbit is dense. And there's a terminology for this in dynamics. When you have a closed set with a dynamical system acting on it, you say it's minimal if every orbit is dense. That means there is no smaller closed invariance set. So this is said to be minimal. So you'll hear the phrase, the horocycle flow is minimal, as the statement of Tedlins theorem. And so the picture should be that although for geodesics, we can have many periodic orbits, if we look at horocycles, every horocycle goes everywhere on the surface. Well, for one thing, there are no closed horocycles. So let's just recall that if you have a parabolic element in gamma, then there are points in the upper half plane which are translated in arbitrarily small distance by gamma. But that can't happen if the quotient is compact. So there are no closed horocycles in the compact case. By closed, I mean horocycles that are just a closed loop. Unlike the case of geodesics, there are millions of closed geodesics. And this theorem has a complement, which I'll call 1 prime, which deals with the case of finite volume. So in finite volume, the Riemann surface can have cusps. These are pictures of X. And then, of course, you can have closed orbits for the horocycle flow. They're loops around the cusp. They come in parallel families. And in the case of finite volume, what you can show is every orbit of the horocycle flow, except for these, are dense. So one says every orbit of the horocycle flow is closed or dense. So we have a kind of a dichotomy the orbits are as complex as they can be, except in the case where they're very, very small. So that's the statement of Tedlins theorem. And this is, let's classify this theorem a little bit. This is a theorem initially in topological dynamics. It's not, there's no statement about equidistribution here. However, it will later turn out there's a deeper theorem, which says that in this case, every Horus cycle is uniformly distributed. And here, every Horus cycle is uniformly distributed unless it's closed. And even better, if you have a closed Horus cycle and it gets longer and longer and longer, in the limit, it becomes uniformly distributed on X. Okay, so these are topological statements, and unlike the statements for the geodesic flow, we can say a randomly chosen orbit is dense by ergodicity. Well, we can also say that for the Horus cycle flow, a randomly chosen orbit is dense, but this is much more precise because it tells us the topological behavior of every single orbit. And in that way, it's a precursor to Ratner's theorem. So this is somehow this is from the 1930s, and it's the beginning of Ratner's theory, which we will describe at least the statement of fairly soon, and which we will use to discuss the proof of the Oppenheim conjecture. And there's many other things which flow from Tedlins theorem. Okay, now what about the method of double cosets? This is our second nice topic. And let me just remind you how this works. So this method is we're going to study the moduli space of pairs of geometric objects in H. Now we could do this in Hn or many other homogeneous spaces, but for the application to surfaces, obviously we need the case of the hyperbolic plane. So let me remind you how this works. So we have our Lie group G, SL2R, plus or minus the identity. And then geometric objects correspond to subgroups here, certain closed Lie subgroups. And the subgroups we focus on are K, A, N, and AN. And K corresponds to a point in H. And the correspondence is very simple. K is the stabilizer of a particular point in the upper half plane. For example, it's the stabilizer of I, when we take K to be the usual group SO2 sitting inside of SO2R. And then we have the space G mod K, which is the space of points. And this is the upper half plane. So this homogeneous space corresponds to this subgroups, and it classifies points in the upper half plane. For A, A corresponds to the stabilizer of a geodesic. That's the geometric object, geodesics in H. And from this, we get this homogeneous space G mod A, which we've seen is the one-sheeted hyperboloid. Or alternatively, a geodesic is classified by a pair of points on the circle at infinity. So G mod A is the space of pairs of distinct ordered points on the circle at infinity. And let me just mention that these are oriented geodesics. And then N corresponds to the stabilizer of a Horus cycle. And the space of Horus cycles can be identified with the light cone, one piece of the light cone, one component. So say the upper piece of the light cone here. But also, it can be identified with R2 minus the origin, up to the plus or minus the identity. And the nice thing about this picture of the space G mod n is the way G acts on this homogeneous space is just the usual action of SL2R on R2. SL2R acts transitively on R2, and N is nothing more. These are the matrices that form 1, 0, star, star. It's nothing more than the stabilizer of this vector, 1, 0. So naturally, the homogeneous space for SL2R is just R2 minus the origin. Because we've modded out by plus or minus the identity, we should remember to do that here as well. And then finally, AN. This is the only two-dimensional group in this list. And G mod AN is the stabilizer of a point at infinity. In fact, it is the stabilizer of infinity in the upper half plane. It's the upper triangular matrices. And G mod AN is the circle at infinity, or if you like, it's the real line with the point at infinity added. Okay, so geometric objects correspond to homogeneous spaces, and then as we saw last time, pairs of geometric objects correspond to double coset spaces. So pairs of geometric objects up to the action of isometry, isometries of H, which is just this group G, correspond to double cosets. H1 backslash G backslash H2, where these two groups will typically be chosen from this list, and they classify the possible configurations of a pair consisting of an object of this type and an object of that type. Often we'll take H1 equal to H2. And since this is up to the action of isometry, we call this the moduli space of pairs of geometric objects. So this space just tells you what the invariants are if you have two objects of a given type. So our first example, which we discussed last time, is if you take K, let me say also just in generality, what does this space look like? This can be regarded as the space of H1 orbits on G mod H2. And that's nice because G mod H2 is one of these spaces here. It's one of the homogeneous spaces we already are familiar with. And then we just have to understand how H1 acts on this space. It acts by symmetries, acting by multiplication on the left. And then the space of orbits you get can be regarded as this double coset space. Now, why do I say it's the space of H1 orbits? Why don't I just take the quotient like we would do for gamma mod H when we form a Riemann surface? The reason is that this space is often not Hausdorff. So let me just remind you what it means to form this quotient space. This quotient is a topological space. What are the continuous functions on H1 mod G mod H2? These are just the continuous functions on G mod H1 that are invariant under the action of H2. Okay, so they're the functions from G mod H1, say to the real numbers, the real value continuous functions, would be the maps to the real numbers with the property that f of hx equals f of x for all h and h2. And what we will see is that in general, these continuous functions do not separate the points of this double coset space. And that's where things start to get exciting. That's where some sort of interesting dynamics can be derived. But let's start with a case where everything works very nicely. So let's do the case of pairs of points. So if we have pairs of points, P and Q and H, up to isometries of H have only one invariant, which is the distance between the pairs of points. And one way to say that is there's a natural map called the distance function from this double coset space to the real numbers. And this distance function is in fact an isomorphism. It's a homeomorphism of these spaces. In this case, the space turns out to be Hausdorff. And it takes a pair P and Q to the distance between P and Q, which is obviously an isometry invariant. So PQ goes to the distance from P from Q. And put differently, if you take the space G mod K, it's convenient to think of it as the unit disk, then the left action of K just corresponds to rotation around the origin. So this is a typical K orbit, Kx in G mod K, and the orbits are circles, and the space of orbits is the space of possible radii. So you can, in fact, you can make a transversal to this space, which is this arc here. In the hyperbolic metric, that arc is just an infinite ray, and it measures the radius of each of these circles. There's a special circle at 0, which consists of just one point, and then all the other ones are non-degenerate. But in any case, the space is Hausdorff, and there's an obvious invariant of a pair of points. So that's to give you the idea of how one tries to analyze these spaces. You say, given two geometric objects, how might I construct an invariant, a natural way of measuring how different they are? And the basic idea is to measure the distance between them. Okay, so let's do 2, which is the space A mod G mod A. So this is the space of oriented geodesics, or rather the space of moduli space of pairs of oriented geodesics. So when you have two oriented geodesics, there's a couple of invariants you might think of. If the geodesics happen to be disjoint, then you can just measure the distance between them. There's a unique pair of closest points, and you could measure this length. That could be a nice invariant to attach to this pair of geodesics. If you were to reverse the orientation of one of these geodesics, maybe you'd like to negate the length, because this is a different type of pair than the pair where they were oriented in the same place. It represents a different coset here, since these are oriented. On the other hand, when the geodesics cross, there is a natural angle associated to them that rotates one to the other. And while sending the forward arrow to the forward arrow, so this is gamma 1 and gamma 2, there's this angle theta that takes over for the role of D. And as we learned when we studied hyperbolic trigonometry, you can put both of these functions into a single, you can package them by a single quantity, which is the following. You think of gamma 1 as being P1 perp, where the geodesics lie on the one-sheeted hyperboloid. They're vectors with the property that p squared is equal to 1. And then associated to any such vector is its perpendicular subspace, the vectors that are orthogonal to it in the Minkowski inner product. This intersects the one-sheeted hyperboloid in a geodesic. And that's the geodesic attached to this point. And so we can write this geodesic uniquely as P1 perp, this is P2 perp. And then we get a natural function from the space A mod G mod A to to the real line. And the value of d of gamma 1, gamma 2, there's really two regimes. They're the regimes where the geodesics don't meet, and there it's given by the cosh of the distance from gamma 1 to gamma 2. But there's different configurations corresponding to orientation, and that changes the sign of this quantity. And then in this regime, there's also the quantity plus or minus the cosine of theta. Actually, there's no sign here because the cosine is determined using the orientation. These two quantities fit together, and they're nothing more than this inner product, P1, P2, in the Minkowski inner product. So the picture of the space of geodesics, pairs of geodesics, is there's the origin, and then from -1 to 1, we use the cosine of theta to describe the geodesics. And then outside of that, we use the cosh of v or minus the cosh of v, depending on orientations. Okay, now there's one problem with this description of A mod G mod A, which is this map is not an isomorphism. This is not to completely describe, this invariant does not uniquely determine the pair of geodesics up to isometry. Now you might think, well, how could that possibly be? If you know the distance between the pair of geodesics, there's only one way to construct that configuration. You just choose a segment of this length and then draw the geodesics orthogonal to it through its endpoints. Similarly here, if you know the angle theta, there's only one way two geodesics can cross at angle theta. But that's not quite right. There's one nuance missing here. There's a certain class of geodesics, pairs of geodesics, which all have the same value in R, even though they're not the same up to isometry. And the question is, which geodesics get mapped to 0? When do a pair of geodesics get mapped to 0? You might say, well, that's easy. That's when the cosine here is of the angle 0. I'm sorry, I put cosine theta. That does not look right to me. Maybe this is sine theta? Maybe I'm using the wrong angle. Anyway, let me just put f of theta here. We can correct that later. But the idea should be, I see, I've actually made a couple of errors here. So, I'm sorry. No, this is actually right. Sorry, this is fine. The question is, what happens when the geodesics come together? Then the angle theta goes to 0, and you go to the point 1. Or when the distance between them goes to 0, then you're taking the cosh of 0, which is 1. So the question is, if you have two vectors, P1 and P2, and their inner product is 1, in other words, if you have two geodesics, and the angle between them is 0, or the distance between them is 0, are they necessarily the same geodesic? And the answer, interestingly, is no. What's another example of a pair of geodesics whose distance is 0? Whose distance and angle are both 0?
They share a point at infinity, yeah. Wow.
Okay, many people, raise your hand if you just said something or if you know the answer. Okay, let's wait till more people are willing to admit they know the answer. Mary, do you want to share your thought with us?
It's just like if they're converging to the same point at infinity.
That's right. So there's one configuration which I didn't draw, which is this one. You have two geodesics which share an endpoint at infinity, but have distinct second endpoints. These are sometimes called parallel geodesics, and if you were to compute them in Minkowski inner product, you would in fact just get one. So it would be as if the two vectors P1 and P2 were the same, but they're not. They're not the same. And in fact, if this point were the point at infinity, then gamma 2 would be n times gamma 1. That is, if we apply a translation to this endpoint fixing infinity, we get a new geodesic which shares an endpoint with the old geodesic. So the orbits of the unipotent group n give rise to parallel families of geodesics. In any case, the angle is 0, the distance is 0, and yet the geodesics are not the same. On the other hand, up to isometry, there's only one configuration of parallel geodesics. So the space A mod G mod A is almost the real line. It's just that this point right here needs to be replaced by 2 points. And the 2 points correspond to the configuration where both geodesics are the same, gamma 1 equals gamma 2, and then this configuration where the pair of geodesics are parallel. So if you have a sequence of points, of pairs of geodesics, and they converge to this point here, if the angle between them goes to 0, the distance between them goes to 0, you can renormalize, that is, change the picture of the pair by isometry so it converges to this picture or it converges to this picture. In fact, you can take this picture and apply an isometry that focuses your attention closer and closer to P, and this picture converges to this picture. So those orbits can't be distinguished by continuous functions. And similarly, there are 2 points here. There are 2 points here which correspond to the same 2 configurations, but with opposite orientations. Sorry, the point 0, I should have said, that's not where the geodesics coincide. It's this beautiful, simple configuration where they meet at 90-degree angles. Okay, so that's the picture of what A mod G mod A looks like, and what you see is it's not Hausdorff, but in a fairly minor way. And also there is a function that almost describes its quotient, but it has to glue together these points. Okay, so now we're going to come to the main topic for today. After all, we want to analyze the horocycle flow. So what we're going to study are pairs of horocycles. So this is 3 n mod G mod n. So let's first analyze this very naively. So this corresponds to n orbits on G mod n, and G mod n is R2 minus 0, 0, mod plus or minus the identity, which is something we just sort of remember at the end. Let's just think of it as n orbits on R2 to start out with. Now, what is n? N corresponds to the group of transformations 1T0, 1. And how does such a transformation act on R2? So let me call this NT. NT dot XY is just X plus TY. Okay, so this is pretty easy to analyze what the n orbits are. If I pick a typical point up here, XY, then the n orbit through this, that is, if I apply n to this, allows me to add any multiple of y to x, but I have to keep the y value the same. So n dot xy is just this horizontal line. Actually, let me draw it in red. So it's distinguished from the coordinate axes. So there's a typical n orbit. And here's another n orbit. And here's another n orbit. Here's some other n orbits. But something funny happens at the origin. What happens at the origin is, of course, that y is 0. So the action of n restricted to the origin is trivial. So the n orbits form these horizontal lines away from the origin, and then they consist of individual points on the origin. Okay, so now you can see that this space is not Hausdorff. Because if we try to make a continuous function on this space that's invariant under the action of n, that function has to be constant on every horizontal line except for this one. But if it's constant on horizontal lines that limit on the x-axis, it has to be constant on the x-axis. And therefore, it's constant at all of these points, even though these represent different points in the double coset space, in the moduli space of pairs of horocycles. Okay, now that should be something that we can understand geometrically. So let's forget about this picture of G mod n mod G, n mod G mod n, and just think intuitively, if we have a horocycle A to 1, we have a horocycle A to 2, how can we measure the difference between them? What invariant can we attach to this configuration? So somebody tell me a way to attach a number naturally to a pair of horocycles. What might you measure? How can I tell this particular picture apart from, say, this picture, where A to 2 is replaced by A to 2 prime? And I have to just use hyperbolic geometry. For example, is there some way to naturally associate a geodesic to a pair of horocycles? Can someone suggest a geodesic that somehow is determined by A to 1 and A to 2?
Like tangent to them?
Sorry?
Maybe like tangent to them?
That is true, that if you have A to 1, you could try to construct a geodesic that's tangent to A to 1 and A to 2. That would be kind of interesting. But then there's another geodesic that's tangent to A to 1 and A to 2. And actually I think there's even one that goes like this, but we'd have to be more careful. But that's interesting, but it's not quite unique. It's a nice idea though. What's another geodesic you can naturally attach to A to 1 and A to 2?
You could do the geodesic ending at the centers.
That's right. So remember, these geodesics, these horocycles should be just thought of as circles, and they have centers, C1 and C2. So another geodesic, even more canonical than this one, is you just draw the geodesic that goes from one center to the other. So that's very nice. That's very similar to the common perpendicular to a pair of geodesics. And in fact, this is a good fact to know. If you draw any geodesic that begins at the center, it meets the horocycle at an angle of 90 degrees. So this geodesic is the unique geodesic that meets both horocycles in 90 degrees. And in fact, these 2 points, P and Q, are nothing more than the closest points on the horocycles. As P starts to slide towards C1, it gets farther and farther from A to 2 and vice versa. So as usual, the nearest points have to be joined by a geodesic orthogonal to the objects in question. And these are the closest points on these geodesics. And so then we could attach to these geodesics this number D, which is just the length of this geodesics. That would be the distance between the horocycles A to 1 and A to 2. So that's really quite a nice invariant that we could attach to n mod g mod n. So we could make a distance function which takes values in the real line. Now there's one little nuance here, which is as we make A to 2 bigger and bigger, it's going to ultimately become tangent to A to 1. Well, that's no big deal, then the distance is 0. But after that, it's going to start going inside of A to 1. And we might get confused here, but it's not such a big deal because we still have this natural arc, subarc of the geodesic that starts on one and ends at the other. It's just it's now inside of one of the horocycles. And in fact, it's inside of both of the horocycles. So when they start to overlap, we can just allow the distance, which became 0 here, to start to take on negative values. So maybe we will use minus d to describe that configuration. Let me just draw it so it's less clumsy to see. If we have two horocycles that are close together, then they still have a natural geodesic joining them, and you can take this distance here with a minus sign as an invariant. So that's pretty good. We have a map of the horocycles to the real numbers. However, there's one type of pairs of horocycles where this construction does not work. When does this construction just not work at all?
When they have the same center.
Yes, exactly. So if C1 is equal to C2, then what do we see? Then we have one geodesic, a horocycle resting on a point, and we have another horocycle resting on a point. Let's suppose this point C is infinity. If the point C is infinity, then in the upper half plane model, what we have is a horizontal line and then another horizontal line. These are our two geodesics. And what happens in this case is that there is a new invariant we can construct, which is again the distance between the geodesics. It's this width here. And this width is constant. It's independent of which geodesic starting at C1 we choose. As you can see very clearly in the upper half plane, these geodesics now these horocycles are now parallel horocycles. And here they really are parallel in the sense that the distance between them is constant as you move along them. So there are no parallel geodesics in hyperbolic geometry, but there are parallel horocycles. And so what happens is when the centers coincide, suddenly there's a new invariant available, which I'll call delta. And what's happening in this picture is that these lines, these horizontal lines here, are the cases where the centers are distinct. So we have a map to the real line where the centers are distinct. Now, as one of these horocycles slides over closer and closer to this one, this number here, minus d, goes to minus infinity. So when you finally reach this configuration, it corresponds to d equals minus infinity. And then there's a whole real line's worth of additional stuff to measure. So you can think of the space of pairs here as being the real line, union minus infinity. But minus infinity actually itself represents a whole real line, which I'll draw like this. And it gets collapsed to one point. So in fact, what happens is that D is very good at measuring the heights of these horizontal lines, but it can't possibly distinguish the points along the real axis. And these correspond to horocycles that have the same center. And so there we have to introduce a new invariant to separate those horocycles. Okay, now let's draw a conclusion from this picture. Suppose I have a sequence of horocycles with distinct centers, but the centers are getting closer and closer together. Say the horocycles are converging. Then actually I can move the whole picture by an isometry so that the pair is represented by any point I like on a horizontal line, and then I can get that representative to converge to any point I like on the real axis. So there's actually a theorem that you can derive from these pictures, which is basically proved by just staring at this image here, although it can also be proved geometrically, which is the following. Suppose we have horocycles eta k tend to, let me call it eta naught, with the centers of eta k never equal to the center of eta naught. Then there exist Gn and G, that is isometries, a Gk and G, such that, and let's say Gk tends to the identity. Sorry, just, I'm saying this wrong. There exists Gk and G. I'm sorry, I'm saying this wrong. Let me see how to say this. Sorry. There exists oh yeah, so let's suppose that n naught yeah, so okay. Let's suppose that for convenience that n naught is the horocycle given by the imaginary part of z is equal to 1. It's our standard horocycle. Then there exists uk in n such that uk eta k converges to the horocycle defined by imaginary z is equal to y. And then let me get the quantifiers right. Then for all y greater than 0, there exists a way to move these horocycles, adjust them by an element of u so that they converge to any given horocycle we like that's parallel to this one. Okay, so let me say this, let me draw the picture of what I'm saying here so it becomes a little bit clearer. So here's my limiting horocycle eta naught, and I have some other horocycles that are getting close to this one, but their centers are not at infinity. However, they're converging to this horocycle here. That means if I look in a fixed neighborhood of the origin, they get closer and closer to looking like eta naught. Now, if I don't change them at all, they would just converge to this horizontal line at height 1. This is y is equal to 1. But the theorem is that I can translate them. And translation here, since the elements of n just act by translation of the upper half plane, it says I can make a horizontal translate of this horocycle so that it converges to the horocycle at any other given height that I like. It converges to any parallel I like of eta naught. So it converges to say the horocycle at height y equals y naught. And the way you do this is very simple. You take the horocycle eta k, which is given by a very large circle, and you look at where it crosses this line, y equals y naught. That might be very far to the right or left, but it's at some point with coordinates minus tk, y naught. And then you just translate the picture so that this point has an x coordinate of 0. So in other words, you can normalize while keeping eta naught the horizontal line. You can normalize by translation. So these horocycles pass through this point at height y0. And the centers are getting farther and farther away, which means the slopes of the circles as they pass through this point are becoming more and more horizontal. And in the limit, they just correspond to the horizontal horocycle at this height. Okay, so the claim is that when you have horocycles converging generically, you can always change coordinates by isometry. So in the limit, rather than one converging to the other, one converges to a parallel of the limiting horocycle. That's the geometric interpretation of the fact that if you have a sequence of n orbits here, you can choose representatives in the n orbits that converge to any point you like on the real axis. Now, some people like the geometric picture and some people don't. So I will say this in an equivalent group theoretic way. And when you read the literature on homogeneous dynamics, often all of these geometric pictures will be eliminated and you'll just see a theorem about matrices. And you can verify the theorem about matrices, but it's mysterious where it's coming from. So let me translate this into a theorem about matrices. So we could ask ourselves, what are these special points here? Well, we just figured it out. They correspond to the following. We start with our basic horocycle at height y is equal to 1. And then these other points are parallels to that horocycle. So what do they correspond to? What are their representatives in G mod n? Well, if you want to get the horocycle at height y equals t, what you do is you take this horocycle here and you apply to it the element, let me call it AT of eta naught, where AT of z is t times z. In other words, you take an element from the diagonal group and you apply it to this horizontal horocycle and you get one that's at a different height. So in other words, these points here, the x-axis, this corresponds to the set of double cosets represented by elements of A. A fixes the point at infinity, just like n does. And when you apply A to a horocycle resting on infinity, it moves it up or down. That's what these points are. It gives you the parallel ones. So the group theoretic statement, sorry, I'm going to have to erase this. It was a little vague anyway, is the following. Suppose we have a sequence Gn going to the identity in G minus An. Then, given A and A, there exists Un and Un prime in N such that Un, Gn, Un prime tends to A. So this is something, I could assign this as a homework problem and you could write down 2x2 matrices and prove it. But let's try to understand geometrically why it's true. We're adjusting G on the right and the left by elements of n. So secretly, these elements Gn are meaningless. All we care about is the double cosets they represent, because we're allowed to change them by multiplication on the right and the left by n. So really, you should say I have a sequence of double cosets tending to the identity, which is represented here. They're in G mod AN. That means they correspond to these horizontal lines, not to the x-axis. They correspond to one of these horizontal lines here because the points on the x-axis are represented by elements of AN. So it's saying if you have a sequence of horizontal lines tending to 0, which is what these double cosets correspond to, you can choose representatives on these double lines, which is what UN, GN, UN prime correspond to, such that these converge to a given point A on the real axis, given that the points on the real axis correspond to the double cosets of A. Okay, so this is a typical theorem that's proved by, that involves this method of double cosets. And the reason this theorem exists is because the space n mod G mod n is not Hausdorff. We're taking advantage of the fact that this single point at minus infinity is blown up into this whole horizontal line to get some action going out of an arbitrary convergent sequence of horocycles. Okay, so now I think we're ready to prove Tedlins theorem. So any questions before we turn to an application of this double coset idea? Okay, so let me keep that theorem there, and we'll now prove Tedlins theorem. And I'm going to write the Tedlins theorem in the homogeneous language. So the theorem of Tedlin, which is called minimality of the horocycle flow, can be stated as follows. So suppose T1, the unit tangent bundle of X, which is gamma mod G, is compact. So of course, G is our Brandessel 2R, mod plus or minus the identity, and gamma is a lattice or a discrete subgroup of G, and we assume the quotient is a compact space. That's the same thing as saying that X, the corresponding Riemann surface, is compact. Then every n orbit is dense in T1X. So remember, the A action on G mod gamma corresponds to the geodesic flow, the K action corresponds to rotating the direction of a vector at a point, and the n orbit corresponds to following the horocycle that's orthogonal to a given vector. And so this says every horocycle is dense. Okay, so what's the proof? So in addition to this lemma, the proof involves the following neat idea. So the first thing we do is we just write down what we want to analyze. We pick a point X in the unit tangent bundle, and we act by n on the right, and then we form its closure. So B and orbit closure. And now we come to a very interesting idea in dynamics in general. When you have, let me do it for a single transformation. When you take the closure of an orbit, the orbit might accumulate on something. And so the orbit closure might be all of these points plus this extra point. And in that case, within the orbit closure, you have a smaller invariant set, which is this limit point. Or in the case of a horocycle flow, you might have some sort of strange subset inside of Z, and it might be that the horocycle through X accumulates on this strange subset, maybe in forward and backward time. And then this strange subset sits inside of Z, and it's much more recurrent than Z itself is. the limit points of this orbit need not be the whole orbit. They might be some smaller closed invariant set. So the observation is the following. If you want to analyze Z and it has within it a smaller invariant set, you might as well analyze that smaller invariant set. Oh, but now this smaller invariant set might have the property that there's an even smaller invariant set inside of it. Maybe it also has this spiraling behavior. So you say, okay, well, I'll just keep iterating that process. I'll get a whole bunch of these guys and then I'll take their intersection. That should be an invariant set where every orbit is dense. Well, it still might not be. And so you're tempted to carry out some very complicated inductive procedure to try to find the smallest closed invariant set inside of Z. And one of the problems is that that smallest closed invariant set might not be unique. Well, there's a standard method in mathematics for handling this kind of thing. It's the axiom of choice. So you see, if you have an n invariant set inside of Z, or if you have a nested family of them and you intersect them, you'll get another n invariant set. And it'll also be non-empty because of the fact that we're assuming T1 of x is compact. Everything is sitting inside a compact space. So by the axiom of choice, there exists a minimal invariant set inside of Z. And what does minimal mean? It means every orbit is dense. You see, if an orbit wasn't dense, then the closure of that orbit would be a smaller invariant set. And so this argument, which I've just sketched in without writing anything down, is usually summed up, because it's so common in the field, by the following quick statement. Using the axiom of choice, we can assume Z is minimal. Every n orbit in Z is dense. So this, to my mind, is the second big contribution to this proof of Tedlins. It's not at all obvious that it's going to be to your advantage to work with a minimal set. And it's not even clear how you would construct one. In fact, you seem to have to appeal to the axiom of choice to construct one. Nevertheless, you can assume this. Now, what is good about minimal sets? What's good about minimal sets is that if Z1 and Z2 are n minimal, then Z1 intersects Z2 is also n invariant, since each one of these is n invariant, but that implies Z1 must be equal to Z2, because these are both supposed to be minimal invariant sets. Every orbit should be dense. So if you have something that's in their intersection, that would be a properly smaller set, contradicting minimality. So when two minimal sets meet, they have to be equal. That's the advantage of this initial step of the proof. Okay, so now we do something rather clever, which is we consider S, which is the set of elements in G, such that when you move Z by G, it still intersects itself. And I claim that there exist, first, I claim there exists Gn going to the identity in S. Gn not equal to the identity. Now, the first thing to notice about this set S is that if I were to put an n on this side of G, it would, if G is in here, so is n times G, because Z is n invariant. But also this Z is n invariant. So if I put an n here, I could get rid of it by putting an n inverse on both sides here. But since capital Z is n invariant, it's the same. So the first thing to notice is that S is equal to NSN. It is a union of double cosets of n. And then there's the second thing to understand is, and this is really miraculous, suppose we take S intersect A. Let me call that SA. Just for brevity, this is just the same as the elements A and A, such that when you apply A to Z, it still meets itself. But remember, A of Z is something like a constant times Z. So when you conjugate the translations by n, by A, you get the translations again. The diagonal matrices normalize the translation matrices. The horizontal flow is normalized by the geodesic flow. So if AZ meets A, then what you'll notice is that AZ has the property that ZAN is equal to ZNA because of the fact that A normalizes N, and Z is N invariant, so this is equal to ZA. So what you see is that ZA is N invariant. And Z was a minimal N invariant set, so ZA is also a minimal N invariant set. So when ZA meets Z, we have an intersection of two minimal sets, so they must be equal. So the elements of S that also belong to A are just the elements of A, such that ZA equals Z. And one of the nice things about that is that this forms a group. It forms a closed subgroup of A. The property of ZG meeting Z is not necessarily invariant under composition, but the property that Z is left invariant by this element A is, of course, invariant under composition. So within this union of double cosets, we have a special subgroup, which is the part that sits inside the diagonal matrices A. Okay, so now we're almost done. Our claim is that SA contains elements AN not equal to the identity, but converging to the identity. In fact, let me just say it like this. Our claim is that SA is equal to A. And let's suppose that we have that. So if that were true, then this would imply that that not only is Z invariant under N, but it's also invariant under this group A, because every element A could appear here. So this would imply that Z is equal to Z times AN. And now there's a fact which I haven't drawn your attention to a lot, but which I'm going to quote here and then say a word about it at the end, which is that every AN orbit is dense. Which is not so unexpected. This is now a two-dimensional Lie group. When we pass to a two-dimensional Lie group, it's very hard for the orbits not to be dense. And in fact, every AN orbit in the unit tangent bundle is dense. So once we get that Z is invariant under AN, in particular, it contains an AN orbit. Those AN orbits are dense. And so this implies that Z is the whole thing. Okay. And then, so then we're done. So the whole proof boils down to showing that this subgroup of A is non-trivial, in fact, that it equals the whole group A. Now, how do we do that? Well, first, I want to show that the set of elements in G that that sends that moves Z in such a way that it meets itself contains a non-trivial sequence tending to the identity. And in fact, it's not only tending to the identity, but it won't be in N. So here's the proof of this claim. Let me draw a picture of it here. So here's the unit tangent bundle of X, and here's an element in Z, and here's its orbit, Xn. So that's its orbit under the horocycle flow. Now, I claim that this orbit has to accumulate on itself. And if it does, that means there are nearby elements in this space, gamma mod G, that are close to this original element X, but are not on this initial flow line through X. And now every element in G mod gamma can be represented as G times any fixed point, G times X. After all, this is Gx transitively here. So I can write this nearby point Xn as X times Gn. And to say that this flow line here is not the same as this one is just to say Gn is not an N. I choose Gn close to the identity, and then it can't be part of this piece of N orbit here. Now, why is it that this orbit has to accumulate on itself? Well, if it didn't, then there would be a neighborhood of this point, which consists just of the flow line through it. But Z is compact, so you would start moving this point along, and you would eventually cover the whole orbit with balls which are just locally pieces of a single N orbit, and then you would get a closed N orbit. So because there are no closed N orbits, the orbit of Z has to accumulate on itself, and so we can get this sequence Gn that moves Z into itself and is close to the identity, and it's not just obtained by flowing along the orbit of the horocycle flow N. Okay, now let's just suppose now that I could actually get that this is not an AN. If I could get that the GNs are not an AN, then I can apply my lemma. Remember, the lemma says that I can choose UN such that UN, GN, UN prime converges to any element in A that I want. But S is invariant under multiplication on the right and left by N. So once I have Gn in S, I also have these elements in S. And then since S is closed, I can get every element of A I want. And so then I get SA equals A, and the proof is over. Finally, what happens if I'm forced to choose the GNs in AN? Well, then I can just factor Gn as AN times UN. And I can, since S is invariant under N, I can just get rid of the UN. And these are tending to the identity anyway. So then at least I get a sequence converging to the identity in A, in SA. But SA is a group. So once you have an element very close to the identity, AN, you have the whole subgroup it generates. And as these elements get closer and closer to the identity, that group gets denser and denser. And since SA is closed, in the end, you get that SA is equal to A. Okay, so that is the idea of Tedlins' proof of minimality of the horocycle flow. And just summing up, there's two major things going on here. One is this idea that this is using the method of double cosets, and the other is this trick of using minimality. But what you might have gotten lost in this presentation, which is very economical from the point of view of using words, is the geometry behind the picture. So let me just try to say in a picture how Tedlins proof works. On the surface, I need a little bit of room. So here's my Riemann surface. And now I have a Horus-cycle on this surface, eta. And the way Tedlins proof works is really this. This Horus-cycle comes along and crosses itself very nearly parallel to where it started. And if you look at where it crosses itself and you start following it along, you can get to a point where the distance between this Horus-cycle and this later piece of the same Horus-cycle is about 1. But they diverge so slowly that when you draw this orthogonal here, then you draw this short geodesic here, it's almost orthogonal to both of them. It's not quite orthogonal because there's an angle here, but this geodesic is nearly parallel to this one. And then another piece of the Horus-cycle comes along and makes an even smaller angle. So maybe you have to wait much longer. And then somewhere else on the surface, you get a separation of 1. But now it's almost exactly orthogonal. So since everything is compact, at the end of the day, you can conclude that the set C contains a pair of orthogonal parallel Horus-cycles, distance 1 apart. But 1 was arbitrary, so you conclude it contains a pair of parallel Horus-cycles distance epsilon apart. And from that, you conclude that it's invariant under the action of A. So that's the geometric picture of Tedlins proof. Okay, so finally, I owe you one thing, which I probably should have done in advance of this, which is a much easier result about dense orbits. And that's the theorem that the AN orbits are dense on the unit tangent bundle of X. So let me state that theorem, which I owe you and which was used as a lemma, was really the key point in concluding the proof. So the theorem is that if T1 of X is compact, and in fact, much less is required, this implies every AN orbit in T1X is dense. And before I prove this theorem, let me make the following observation. So whenever you're studying dynamics on a homogeneous space, there's a way to shift your point of view if you prefer. And what we're discussing here is the orbits of AN acting on gamma mod G. But if you like it better, you can look at gamma acting on G mod AN. And what is G mod AN? This is just the circle at infinity. So this theorem is equivalent to the following statement, which is every orbit of gamma acting on the circle at infinity is dense. And let's, before we sketch the proof of this, let me just give you an example and a picture to make it clear that this should be obvious. So one example is let gamma be SL2Z and let the point P on the circle at infinity be infinity. So what is gamma dot p as a subset of the real line? Well, it's the image of infinity under Mobius transformations of the form AZ plus B over CZ plus B, where A, B, C, and D are integers. Now, what is the value of this Mobius transformation when we put in Z is equal to infinity? What is the image of infinity under this map?
A over C.
It's just A over C. So to say that the orbit of infinity is dense is to say that the set of ratios of entries in the first column is dense in the real line. Now, why is that true for SL2Z? In fact, the orbit of infinity is equal to the rational numbers union infinity, and therefore it's dense. Why does every rational number arise from a column of a vector in SL2Z? Well, let me remind you that if you start with an arbitrary rational number, then you can write it as A over C, where the GCD of A and C is 1. Since we're in a UFD, we cancel out primes and we get a pair of relatively prime elements. Now, what does it mean to say A and C are relatively prime? It means the ideal generated by A and C inside of the integers is everything. It's the ideal generated by 1. And that means you can find other integers such that AB minus BC is equal to 1, which means exactly that A and C occurs as the column of a matrix of determinant 1, i.e. an element of SL2Z. So that's a quick proof that the orbit of infinity is dense under the action of SL2Z. Well, I've already gone a little over time, so I'll explain this fact, which is quite easy for general groups next time. Anyway, that underpins the argument of Tedlin. The whole idea is to promote the n action to an an action, and the orbits of an are easily seen to be dense. Okay, so we'll continue with that next time. And I remind you again, my office hours are tomorrow. They're at 3 unusually, and do please come by tomorrow or some other time.